Hey, what's up YouTube? It's BetaPlayer1011 here, and today we'll be doing a crash course on, basically an introduction to calculus, all the stuff you need to know to actually do calculus. Now, a lot of this should be reviews, so this means that I'm not going to go slowly through a lot of this. I'm going to go very quickly, or relatively quickly. So, first we're just going to review the basic definitions of what a function is and the different things you need to know about functions. So, first, a function is basically where you input something into a certain function and then you get an output value. So, it's written generally like this, where f of a being the input, you get b. So, let's say you have the equation y equals x squared. So, you input some value 1, let's say, into this x squared function. You input the 1, so you get that 1 squared is equal to your output value, which is 1. Now, over here you'll see a graph of just a function. It's not any particular function. It looks a bit weird, but this is to demonstrate some important concepts. First, the concept of increasing. So, on this interval over here, starting from over here and ending over here, this function is increasing, so it's going up. Then it starts to decrease as it goes down, and then it starts increasing again. Now, the point at which it changes is called a maximum or a minimum. So over here, it's a relative maximum since it goes up and then down. Here, it's a minimum because it goes down and then up. The next thing is concavity. So over here, you see that it's like down-shaped. Over here, like it's like this. This means that it's concave down over this entire interval. Over here, it's like concave up because it's opening upward. So the mouth goes up, the mouth goes down. That's concave up and concave down. Second to lastly on this function over here are zeros. So a zero of a function is where it crosses the x-axis over here, where when you plug it in, plug in the x value, you get a 0. So if I plug in 0 for here for x squared, I would get 0. That means that the 0 of the function is 0. And lastly, a domain and a range. So every function has a domain and a range. A domain is all the x values that would work. So for a lot of functions that you'll run into, the domain for the function is all real values. For example, every polynomial function, like for here, for x squared, you can plug in any x value. However, let's say I have 1 over x. If I plug in 0, 1 over 0 is undefined. So that wouldn't be in the quote-unquote domain of the function. And then the range is the output. The output being the range means that what are the values that this could lie on. So for polynomial functions, again, it's either every real number or just like half of them. For example, for x squared can never be negative, so the range is always going to be between 0 and infinity. However, if it was x cubed, that can be negative, so it's from negative infinity to positive infinity, or all real numbers. Now, I hope that makes sense. I'm sorry if I'm going like too quickly. The last thing I need to cover on functions are just what even and odd functions are. So again, this should be a review. So an even function is where it's can be reflected across the y-axis. So over here I drew a popular even function being the cosine function. So as you can see, if I go here, these values, if I reflect them across the y-axis, I literally treat the y-axis as like a line where I rotate this entire thing over. It's literally the same thing, right? So the mathematical definition is that when I plug in negative x into the function, I should get the same thing I get if I plug in the positive value. So f of negative x equals f of x. So here, f of negative x being, let's say, negative whatever this number is the same thing over here, or here and here. Now, for polynomials, every function that only has even integers, hence even function, is an even function. Now, for odd functions, if I plug in f of negative x, I'm going to get negative f of x. So what this means is that it's reflected over the origin, or just over the 0, 0, 0 point. The origin is literally just the center point over here. Now, you can imagine that if I draw this line over here, it's like reflected across this line. That's the kind of the way I imagine it. So if I go down this way, right, if I have negative x here, this value over here will be the negative value of this value over here at positive x. So this is a sine function. That's a popular odd function. An odd function is also when you have a polynomial with only odd integers. Anything else is just neither. But these have special characteristics that help us quite a lot. Now it's moving on to two special functions. This is called the absolute value function, where let me change that. Oh, I forgot to do one more thing. So I'm sorry for jumping back, but there are two tests to determine whether a function is a function. First of all, the vertical line test. A function cannot be a function if, for example, a circle cannot be a function, because if I have f of x, I could have two possible y values. Let's say if this is our coordinate plane. On this x, it could either be negative y or positive y, for example. So we have to do the vertical line test, and if a vertical line never crosses 2 points, then it is a function. Now, a one-to-one function means that its inverse is also a function. An inverse means that we literally just switch these axes. This is the x-axis, now this is the y-axis, and you could just like flip the paper over basically. But without doing that, what we're going to do is we're just going to do what we call the horizontal line test. And that would mean that we literally just do horizontal lines across the paper. Whoops. Like so. Now, as you can see, this does not pass the horizontal line test. It crosses 3 points on this horizontal line. So it's not a what we call one-to-one function. Moving on. So these are two special functions. This is an absolute value function. Means that all the negative values of x are positive. So we denote that by using these two straight lines. And as you can see, this line over here, when I plug in the negative values, it's actually the positive x values. So it just becomes this straight line over here. And over here, this is a point where it's like the slope changes. So here, it's just regular x. Now over here, when you plug in negative x, you change these x values to positive x, and what you get is that you get the same y value over here that you get on the other side. So it's basically this reflected. The greatest integer function is, by definition, the greatest integer up until that point. We denote that by this symbolism. So f of x equals x with a line on top of it. So, for example, I'm going to start at 0 and go to 1. Now, on every value between 0 and 1, I get a bunch of decimals. The greatest integer up until that point is 0, because let's say at 0.99999 over here, it's not 1 yet. So the greatest integer up until that point would have been 0. For everything above 1 up until 2, at like 1.99999, the greatest integer up until that point would be 1. So every value here, the greatest integer would be 1. So what we're going to do is we're going to draw a circle here and then do a dotted circle over here. This means that at 2, the greatest integer is 2. So this circle means that as you approach it, it's 1, but at 2, it's 2. And if you approach it on the left side, or going from the right side, I mean, it's 2. So the circle just means that at 2, the value is not 1, it's actually 2. The dotted circle means that it's 2. Moving on, we have polynomials. So polynomials take the form of this, where you have a being a coefficient, just any number, times x being the variable to an nth power, and then we add will be a different coefficient times x to 1 power lower, and then this goes on and on and on until you hit some constant c, which has no x value. And these are just some examples of polynomials. So the special thing about polynomials is that literally every x number fits into this equation. You can plug in any x value you want. So the domain is all real numbers. So over here, you have x, f equals x. This is just what we call a linear function. So I'm going to draw f of x equals x. Now over here, it's a what we call a quadratic. So f of x equals x squared. And over here, it's another special polynomial. We call this f of x equals x cubed, so it's a cubic function. Now, if we look at the end behavior of these functions, for all the odd ones, all the odd-powered ones, it approaches positive infinity as we go to positive infinity, and it approaches negative infinity as we go to negative infinity. Same over here. Over here, it's squared, so it goes to positive infinity on both sides. Because when you square something, for example, the square root of not the square root, the square of negative 2 is just 4. The square of 2 is also 4. However, 2 cubed is 8. Negative 2 cubed is negative 8. So, hopefully that makes sense on polynomials. Next, we just have a little crash course on trigonometric functions. This is a sine function, which you saw earlier. So, the sine function, trig functions are just repetition. So, a sine function goes like this. A cosine function is literally just a sine function, just shifted over a little bit. So if you go like this, you can see the sine function over here. I'm going to draw that in a different color. You can see the sine function over here, right? But it was just shifted over by like pi over 4. So by pi over 4, pi over 2. So yeah. The cosine function starts at 1 and drops to negative 1. The sine function starts at 0, goes up to 1, drops to negative 1, and goes back to 0. And they repeat. So if I drew it over and over again, as you can see here, it would just be a repeat of the same curve. Tangent looks like this. So the difference between tangent and cosine and sine is that sine usually occurs on the interval of 0 to 2 pi. And then tangent over here, this goes from pi over 2 to pi over 2, well, negative pi over 2, my bad, to pi over 2. So that means that this entire curve happens on the interval of 0 to pi, or well, on an interval of a distance pi. This one occurs on an interval of pi. Now, two last things we need to review is just the basic form of the equation. So, all these functions were just their regular form, which is that you have sine of x, or this could be cosine or tangent. However, it could look a little bit different. So I'm going to draw a little bit of a more complicated looking thing. So you have a sine of, I'm going to do f x. I probably shouldn't use f, but I'll explain that in a second. Plus phi plus c. So all trigonometric functions can take this sort of form. A is the amplitude, meaning that this is the highest it can go. For example, let's say the amplitude here was 10. So the distance between this 0 point and here is 10. We call this 0 point the equilibrium. So the amplitude is just the highest it can go. Then you have your function, sine, cosine, tangent. This tells you the angular frequency. So let's say this number is really high. Then you get a trigonometric function that looks more like this, where it oscillates really quickly, rather than something that goes like this and takes a long time to complete. X is your variable. Phi is your phase shift. So if you add it, you're going to go, now this is weird, in the opposite direction. And then if you, let's say, subtract it, you actually go to the right. So I always remember these phase shifts as the opposite. The phase shift just means that, let's say you add 5, you go to the left by 5. You shift this entire function over. See, this just adding it's another shift. It goes up or down. This is something that makes a little bit more sense. If you add it, it goes up. If you subtract it, it'll go down by whatever value you specify. So that's because you have the regular value here for these functions, but then you just add 1, so you have to shift all of this up by 1. For example, tangent of 0 is 0, but plus 1 would mean that tangent of 0 plus 1 is 1. All right. Now, here are exponential functions. So this is very important over here. That's why I wrote it out initially. Converting between an exponential form and a logarithmic form. Now, you have, let's say, 5 to the x equals 10. Now, I'm sure maybe you could do this in your head. I don't think most people can. So what you do to get this x out of there is to convert it into a logarithmic form. So we have log of a. So in this case, our a is 5, so base 5 of b. B is your answer, so 10 is equal to c, which is the exponent. So the exponent is x. So you could plug this into your calculator, or if you can do logs in your head or whatever, you can do that too. So log base 5 of 10 is x. Now, one of the most famous log bases is log base of e, of whatever value x. We changed that into the natural log of x, just ln. So ln of x. Over here, I wrote out the rules for exponents. Anything to the 0 power is just 1. So over here, this is an exponential graph, by the way. This is 1. A to the 1 is 1, so 5 to the 1 is 5. 6 to the 1 is 6. When you have two of the same bases with two different exponents being them raised to, you just take one base and add the exponents. So 5 to the 2 times 5 to the 2 times 5 to the 3 is 5 to the 2 plus 3, or 5 to the 5. Dividing is the opposite. You subtract. And these are what the graphs looks like. This is an exponential function, and this is a logarithmic function. Now, what you get to see is that this one is just the inverse of this. So the inverse of the exponential function is the logarithmic function. All right, last thing is parametric and polar equations. So thank you for sticking with me this long. I know the video is kind of long. Parametric equations are very simple. You have y and x being set to a parameter t, or a different value. So usually what you'll want to do is you'll want to bring this back into a form of y equals x. So what you'll see here is that x, so we're going to subtract 1 on both sides. So minus 1 plus x equals t. And then you can just take this and substitute it back into this. It's that simple. So what you get is that y equals x minus 1. So this is your parametric set of equations, two equations. So you know how they change with time. And this is just your y in terms of x. Polar is a little bit more complicated, so I'll spend a bit more time on this. So you have r, y, and x. This is how we change between different coordinate systems. So this is what we call the Cartesian coordinate system. What we've been dealing with this entire time. We just have y here and x here. Our goal is to change it to polar. So polar is a coordinate system that looks like so. You have, I messed it up already. So basically what you're going to see is that the polar coordinate system is based on circles, and we use them mainly in trigonometric functions. So you have an r-axis just like this, but then after that, you have to raise it to some theta, some angle on a circle. So you're going to have a system that basically looks like this. So let's say r is equal to 1, so I put it here, 1. And then theta is 30 degrees, so I raise it up 30 degrees, and that's my point over here. Let's say r is, I'm going to make it a different color, 2. And I raise it to 180 degrees. I go 180 degrees, so I go all the way across over here, and my point lands over here. So how do we convert between these two coordinate systems? R is basically just the straight distance to the line. Rather than breaking it down like you move this way to the right and then up 2, you just go straight there. And what we notice is that this is a right triangle, so we use our Pythagorean theorem. X squared plus y squared is r squared. Therefore, r is the square root of x squared plus y squared. Y is the vertical line. So we know that sine is opposite over adjacent. So opposite over hypotenuse, my bad. And the hypotenuse is r, so we just move that over here. So the hypotenuse multiplied by sine theta gives you y. And in the same way, cosine is just adjacent over hypotenuse. So hypotenuse in the denominator, multiply that. You get that hypotenuse times cosine theta is x. And just by using these three formulas, you can convert any Cartesian coordinate system into a polar coordinate system. And that's just a really quick crash course on the basics of calculus. So I'll go a little bit slower in the future for calculus principles because I'm assuming that those are new rather than this, which should be review. I hope you enjoyed the video, and thank you for watching.